Good morning, everyone. This is Dave D. Hilster from Dissident Science and also the John Chappell Natural Philosophy Society. And you're here this morning to watch us interview and talk with Dr. James Maxlow. And he's going to be on in a little bit. But again, you have tuned in to the Saturday Science Chat. Hey, again, I'm Dave D. Hilster, and if you're not a critical thinker, well, or if you are a critical thinker, you've come to the right place either way, because, of course, I'm your science therapist trying to get you to the promised land, not to tell you what truth is. I can't tell you what that is. No one can. You got to figure that out on your own, but we can certainly try to guide you. That's what I'm here for. And today we have absolutely fantastic show. One of the greatest scientists of all time, but also the greatest geologist who's ever lived. Yeah, you can write that down, put it in your what do they say? Put it in your pipe and smoke it, whatever they say. But we're going to be talking with Dr. James Maxlow. He is in his fourth of his series of talks on expansion tectonics. It's always great. He's always a great speaker. And of course, he is going to be next year, 2021, 11. I don't even know what years they are anymore. But we founded our John Chappell University of Natural Philosophy. He's going to be one of the professors, I guess you can say there, and he's going to be putting together a course in expansion tectonics. But before we move forward, of course, I always present who are we, what are we doing? Science, of course, I've said this is Saturday Science Chats, and it is sponsored by the John Chappell Natural Philosophy Society and Dissident Science. I want to welcome all my Dissident Science subscribers out there, getting close to 3,500. It's great. And of course, we're getting close to 1,000 subscribers in natural philosophy. So you can, I want to thank both of those organizations for being part of the Saturday morning chats. And of course, the CMPS mission, this is the formal organization that we put, I guess it started formally in the early 1990s. So it's been over 20 years, is it? Yeah, I guess so. Anyways, we are an organization that above all promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside the mainstream, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, and other things such as structures, to provide a forum for presenting serious papers and theories without fear of censorship, and to be run and controlled in its entirety by its paid membership, including the election of its directors and by its members. So that's what our organization is about, because I am part of it. I'm one of the directors. The community, if you want to find out where our community of critical thinkers are, you can go to naturalphilosophy.org. It's a really great site. We got a great new website. We keep getting more and more people. It's an active website. You can go there, and there's a lot of great discussions that you can jump in. And there's certainly somebody's going to say something you don't agree with, or you agree with, or you need to discuss with. And that's what this new website is all about. It's fantastic software. It's called BuddyPress, based on WordPress. So you want to check that out. It's great. Of course, how do you participate and support us? Well, you can sign up on naturalphilosophy.org and consider becoming a member. Memberships are annual, and that's the reason we exist. That's why we're here, and that's why we have what we have today, including this live broadcast. And of course, we have participating in community discussion on the website, like I said, and of course, you can post news and happenings about us on social media. Folks, I'm going to show you a little later on this, before James comes on, about if you don't think social media makes a difference, then you guys are wrong. And I'm going to show you that in spades today. Our websites, again, our community is at naturalphilosophy.org. We have an online magazine, which is very useful for our community. The reason it's useful is because if you are very new, if you don't know what dissident science is about, you don't know that there are critical thinkers that are going against mainstream science and who are not the crazy people who just say everything's wrong, this is right. People who are actually critical thinkers have looked at the mainstream science, and thousands and thousands and thousands of us have realized there's so many problems with it. Well, you can go to, and you don't are not a technical person, that's an online magazine for critical thinking, and that's where you can read it just like a regular magazine, and you get introduced to the problems of mainstream science and the great scientists who are going after and trying to come up with new ideas, new models, etc. We also have a Wikipedia that's based on MediaWiki, which is the same open source software. We have over 10,000 pages there, so you want to check that out. And of course, coming soon in 2021, it was opened in 2018, but it's been under construction for a long time. But that's the Chappell University, which is going to be providing courses in natural philosophy. No, you can't get a degree from it, but you never know in the future. And of course, James Maxlow is going to be one of those professors there. But I started this new section, and it's working out pretty well because I can throw together during the week. I see all kinds of things going on, and it hits me, so I try to put these in here and talk about it. But really, critical thinkers in science news, you're going to see anything like this anywhere else, really. So on our community news, you can always find really great things because people post. It's very much like Facebook, but again, it's Buddy Press. And Stephen Hurl, which is Hurrell, who is a person, a very big name in Expansion Tectonics. He noted, and this is really true, you can see the little icons up there. In fact, I know how to do this now. I can get my laser pointer. There we go. There's the laser pointer. And if you see it dancing around here, you see it's the holiday season. And he reminded everybody yesterday was Black Friday, and that his book was on sale. And so one of the things you want to remember, there are a lot of great people, a lot of great critical thinkers. There's a lot of great books out there. If you don't know what somebody to get you a present, have them get Stephen's book, The History of Earth Expansion, or have them get, James Maxlow's book, or Borchert's book, or anyone else's book out there that you perhaps are interested in. Wouldn't maybe buy for yourself? Hey, great gift, or a great gift for somebody who is a critical thinker. Here's some of the discussion going on. Very interesting. I told Glenn Borchert's actually part of this. I told him, hey, Glenn, they're talking about you. So this is Andy. He's a new guy who just registered, and he's talking about the 10 assumptions of science. If you missed Glenn Borchert, we had an interview with him just, I think, last week. I think we had two of them already. I can't keep track, but we're going to have a third one of his on infinity, his infinity, what's that? The infinite universe theory. There you go. And so he's talking about that, so you can see some of the discussion on there. Again, go and participate. Here's something interesting. I'm on Facebook. Why? Facebook, oh, that's useless. People just pick. No, it's not, folks. Again, I'm going to show you that there's a lot of stuff. You get a lot of traffic on Facebook. That's where people are. And it's like a giant 2 billion person room full of people. And you have Dominique, who I showed last week, I believe, who was took the orange and cut it and then opened it up and put it on a bigger. Boy, you should check that out, James Maxlow. You got to check that one out. If you haven't checked that out, the orange peel being cut and then put onto a bigger stuff. It was one of the best from smaller to bigger. I thought I was trying to do that myself, clay and all this. This guy, I think, nailed it. But anyways, he also, he's not an expert in the field, of course, in geology, but he mentioned this article that he found on the positive growth of continental crusts. And Steve Hurl there, with I guess he's got his COVID mask on, I can see there. He said, good find. Many comments in the paper clearly show the data is constrained to a constant diameter Earth. I think that's what they're calling about GPS gets kind of, they keep adjusting it, thinking it's just, I don't know what they think it is, but obviously people in Expansion Tectonics know probably what it is. So that's going on. And again, here is very interesting. I hang out at Albert Einstein's Facebook page. Why do you do that? Well, there are 19 million. Actually, it used to be at 21 million. They're losing people because Albert Einstein isn't relevant anymore, even though he's in the news all the time. But anyways, I make so many comments there. I became a top fan. Okay, all right. I mean, I'm the guy who came up with I spent 9 years of my life on the documentary called Einstein wrong. Why would I be on Albert Einstein's page? Well, to sort of point out there in a nice way. I don't go there and call people names or anything. I go and point out. For instance, they get stuff on dark matter. It goes, dark matter is the next fame machine. Here's what I put in Facebook, right? This generated 23 replies. Pro, and people, I'm warring it out there. But this brings people to our page, brings people in our direction, because there's a lot of people who also doubt this. So I put in this comment, dark matter is the next fame machine, even though it does not exist. It's amazing how constant repetition makes people believe in fairy tales. Now, of course, I back that up because I made an entire video. Those who are my subscribers to Dissident Science, and if you haven't seen it, it was one of my better videos. A second galaxy without dark matter, Newton explains. We've had several of our scientists, Cameron Ribisksall. If you haven't seen that, I talk about that. If you go look up dark matter and dissident science, take a look at my video. I talk about that. I talk about his work showing that Newton explains the galaxies without dark matter needed. Also, my father does the same thing, points out some very interesting observations that also point to the same thing. And then, of course, they found two galaxies that don't have dark matter. And guess what? They're spherical. So what does that mean? Well, when you look at the gravitational fields of spiral galaxies, they're not spherical. They have just like a funny asteroid that looks like a barbell doesn't have a spherical gravitational field, just like the moon and the earth together. If you get far enough away, you can put a mass. No, they're not it's not a spherical gravitational field. When you look at galaxies, they're not spherical. And it just so happens that when they measure the speed of stars in a spherical galaxy, Newton works. Well, Newton also works in a spiral galaxy because the field is okay. I gave you all the answer, but take a look at it. Anyways, so when I go out there and say dark matter doesn't exist, I'm trying to back it up with some ideas. And of course, we have a person, I'm going to reveal who this is. MARYELLEN Smith, sounds like a made-up name. Well, it is. I don't know if this article is accurate, but David will probably win this argument when the dust has settled. So you can see I generate people, generate interest. I put links to our work. I put links to Science Woke. I put links to my YouTube channel, which of course links back to all of us at the CMPS. So this fight is out there and it brings people our way. Believe it does. And of course, here's an interesting, just a side story that I've been going. I have discovered that MARYELLEN Smith, his real identity is this guy here. And I didn't put his name down. Oh, gosh darn it. I did this slide this morning, but this is a guy who's actually the owner of Albert Einstein. Of course, this is an article about a 26-year-old who is in charge of the Einstein page. Well, I believe very strongly that MARYELLEN Smith, which is how much more of a made-up name can you have, is really the guy who runs the page, and he makes a lot of money. If you have a Facebook page that has 19 million people, you are making tens of thousands of dollars. You're making your living off of it. So his job is to make sure Einstein stays around because he just happened to claim Einstein's page. Einstein's dead. He didn't do it himself. So he's linked up with the people in Hollywood who are making films about Einstein. They paid him a lot of money to be able to use that Einstein's page to advertise the Genius series. I don't know if you remember that. Einstein himself willed all of his image and all that stuff to the Israeli university, and that, of course, makes a lot of money. In fact, he was the second most making the most money of dead celebrities. And if you look at the article, it says here, talking about this guy, I think he's 31 now. What do Albert Einstein, Kim Kardashian, Taylor Swift have in common? Does this tell you a little bit about really the reality of Einstein? It ain't science. It's money. So anyways, this guy and I are fighting constantly, and he puts up links to me about some kook page. But if you look me up in Google, it's actually quite good. In fact, if you look other people up in Google, it's quite good too. Now, we have our Wikipedia, and we have Science Woke. If you're a person that believes your work should be in Science Woke, one of the featured scientists of our group there, or a featured science like James Maxlow is, Glenn Borkert is, it matters. Go right now, if you're on your computer, Go to a browser and type in Jeff Yee. You are going to see Science Woke. You're going to see this thing come up, and you're going to see Science Woke scientists come up on a Google of his name with his picture. Here's another one. Just Google Glenn Borkert. So you put in Glenn Borkert, the first thing comes up is Science Woke. The second thing is Amazon's book. The third thing is our Wikipedia. Here's one of the greatest, if not the greatest philosopher of our generation in science. You look him up, comes to our websites. Here's another one. Laurie Gardee is a computer scientist, fractal comes, blah, blah, blah. This entire thing comes from Science Woke. So if you want to be known and you don't care about Facebook, you don't care what's going on, these things matter. Make sure your Wikipedia is up to date. I use it all the time when I'm fighting the good fight in the Einstein world to get people in our direction, people who are critical thinkers. It truly works. Now, of course, you can also look up James Maxlow, who we're going to be talking to shortly. And he's got his own website, jamesmaxlow.com, but we have that registered. Expansion Tectonics, we'll talk more about that. But you can see that. And also, the second, one of the other things that comes, actually, this is further down on the list, but if you go not on the first page of a Google search, you will find Science Woke, Dr. James Maxlow. And you also find that James Maxlow receives a Lifetime Achievement Award. So, these things matter. Social media matters. This is where people are. You can sit there and say, no, I'm an old guy and this is not the way I work. Well, you know what? The world's going to leave you behind if you don't do it. So, and then another interesting thing. I have what's called malware bytes. Malware bytes is a great. I'm a computer guy. If you have a computer, get malware bytes, put it on your computer. It helps save you from going to bad websites and all that. It also has information, even from a long time ago. I literally this morning, I updated the database for Malwarebytes to say, hey, protect me, Malwarebytes, from going to bad places. And it said, natural philosophy website blocked due to reputation. Now, yes, you can do conspiracy theories and think that naturalphilosophy.org is blocked because we are going against mainstream science. Could be true. I'm not going to say that isn't part of it. But the truth of the matter is, because we were, and because we have been on the internet for a while, 1998 really, for over 20 years, we did get our server, which was my own server, which was on. I have my own server on the internet. This was different now. We have our own server. It's not on mine. It was invaded by a hack group, the Anonymous group, if you remember that, from Brazil. And they had it out me and a couple of reasons. One was for the science, and they planted themselves on us, and I tried everything to get them off till eventually I had to move the entire server. It was a real big mess. Well, that kind of thing stays around, and there it is. Yeah, but it allows me to continue to site, thank goodness. But I will certainly try to dispute that. But that's interesting. Also, finally, I want to thank our new memberships that we got in November. Some of them are here today. I know in the green room. Thanks you, James Keene, Ian Cohen, Harry Jack Muser, James Marison, and a lot of other people from October and September. It matters. In this coming month, 2 weeks, we have a bill of $700. We've got more than that in the bank, but not too much more. But it can continue very easily. Those are our biggest bills coming up if everyone participates and becomes a member. Come on, guys. You can do it annual, 35 if you're 65 and over, 50. And we have other memberships too. We do have people that do that. We have people who give us thousands of dollars. We've used a lot of that money to get our initial websites up and running. Now we're in sort of a mode. Every month we have about $70, not including the website, so about $130 to $150 every month. So it really, really, really matters. And I want to thank everybody who's made the investment in this, because it's really working. Last week, I believe we had 60 people, I know it doesn't sound like it, but live watching us. We haven't had that for many, many years. So it's really happening more and more. This weekend, of course, is Thanksgiving weekend here in the United States. A little bit slower, but we still have a lot of people on. And I want to thank you again. Please, please, please consider becoming a member. And if you're watching this and here all the time, shame on you. Try to participate and help us out. Okay, we're going to be talking again with Expansion Tectonics, the fourth in a series with Dr. James Maxlow, a PhD. If you don't know who he is a retired professional geologist who has worked as a mining and exploration geologist through much of Australia. So he was out in the field there, of course, and during that time he returned to Curtin University of Technology in Perth, Western Australia. That's WA. If you hear him say WA, that's what it means. I will translate Aussie for you, just so you don't know. Yeah, me. From this research, he gained his Master of Science degree in 1995, followed by a PhD in 2002. If you haven't visited his site, Expansion Tectonics, it is the best site for Expansion Tectonics. Of course, you can go to our Wikipedia. He's got a great information there, but you can go there and really see what's going on and what's happening in the Expansion Tectonics and all about his work. You can see his models up there, which are quite fantastic. And if you haven't gotten this book, this is a great gift. Hey, people, I don't know how much it costs. It can cost, I don't know, $40, $50. It's well worth it. It's a great, great, great book. If you're a science lover, you can easily read it. Yeah, it's got a lot of geology in it, but it's pretty interesting. You don't need to know necessarily the technical terms, but it certainly is the book in geology. So you want to check that out, Beyond Plate Tectonics. And it is just as stimulating to those people who understand that scientific discovery will never be finished. And I think that's it. So I'm going to get out of here, get out of this, and we're going to bring on just shortly Dr. Here he is, Dr. James Maxlow. How are you?
Hi, David. Good, thanks. And I'm glad you incorporated my name in your presentation there.
Oh yeah, no. I mean, I appreciate you coming on. So we do our best. It's part of the membership. So the membership pays for this, and yeah, I don't know why, but people ask for you to come back. I don't understand that, but for some reason you are a draw for us. So I'm actually not interested in any of your theory. You just bring eyeballs to our program. So whatever, no, that's not true at all. Very much. I am a student of your work, and of course, for those who he does remind me, this is your a website, Expansion Tectonics, and thank goodness the person who owns that is the guy who coined it, which I'm not sure is. I think that must be pretty rare in the world of even of the internet, right? Usually people grab a hold of these things, but fortunately or unfortunately, no one grabbed it before you. That would have been great because I think it's worth it. Now, natural philosophy, we had to pry it out of the hands of somebody. So, anyways, you have a fourth of your series, correct? Of your series on Expansion Tectonics. This is the last one today, and I guess if you are ready, I can. Have you, do I have to do something here? Let me see here. Let me remove, I think I have to, okay. No, I think you can share, can't you? So we're going to have him share his screen. He's going to be doing the slides from his side. I think he has actually two screens. So go ahead. I have to stop sharing here. I'm doing that. So I see that, and I've got you sharing. So without further ado, Dr. James Maxlow, let me get rid of some of these, get myself out.
So you're sharing now, David? Okay. Hello, everyone, and welcome to my fourth and final podcast for this series on Expansion Tectonics. In my earlier podcasts, I focused on modelling seafloor and continental crusts in order to create scale models for the ancient Earth, extending from the present day back to the Early Archaean. From this spherical modelling, it was concluded that the extensive geological mapping evidence and empirical modelling studies more than adequately demonstrate that an increasing radius Earth is indeed a viable and demonstrable tectonic process. From there, I began to layer modern global observational data onto each of the spherical models in order to test whether or not this data quantifies the small Earth modelling. The primary focus of this talk will be to continue layering modern global observational data utilised in my research studies in order to further highlight how this data quantifies expansion tectonics. As can be appreciated, up till now, this modern data has only been investigated from a conventional plate tectonic perspective. And from this perspective, if the data doesn't fit the theory, then it is common practice to propose an ad hoc theory to make the data conform. With this in mind, I must once again emphasize that the research presented here is a data modeling exercise, not a theory modeling exercise, which focuses on modeling modern global observational data independently of any present or pre-existing theory. As previously introduced, on an increasing radius Earth until the end of the Permian period, about 250 million years ago, about here, there were no modern oceans, only ancient continental seas. During that time, ancient continental crust existed as a complete crustal shell encompassing the entire ancient Earth. In this image, the distribution of ancient continental seas is shown on the small Earth models, plotted from published ancient coastline data. These seas define the distribution and evolution of the ancient Panthalassa, Iapetus, and Tethys seas over time. On an increasing radius Earth, the outlines and configurations of the exposed lands making up the supercontinents are then dictated by the presence of and changes to these ancient seas. The transition from ancient seas to modern oceans only came about when the Pangaean supercontinent first started to rupture and break up around 250 million years ago. Small Earth modelling also shows that the volume of ocean water has been increasing steadily since Archaean times, and most prominently since crustal breakup and opening of the modern oceans. Complicating this process is that major changes in sea levels also occurred during merging of two or more ancient continental seas, as well as during breakup of the ancient supercontinents and opening of each of the modern oceans. Major changes in sea levels then represent a realistic mechanism for periods of mass extinction of ancient plant and animal species. Small Earth modelling studies show that over the past 500 million years, there have been a number of drastic and prolonged changes to sea levels coinciding with each of the 5 known major extinction events. These extinction events were not instantaneous, as is often depicted in the media, but are known to have lasted for tens of millions of years. On small Earth models, these major changes in sea levels are shown to occur as a result of separation or merging of previous ancient continental seas, as well as onset of geophysical activity and orogenesis, breakup of the ancient supercontinents, opening of the modern oceans, and draining of the ancient continental seas. Depending on the severity of these events, these changes may have also adversely affected regional to global scale climate, as well as ocean water circulation patterns, species habitats, and the type and location of sedimentary deposition. Extinction during the End-Ordovician is shown here on the Ordovician and Silurian models, and this event is known to have occurred over a 10 million year timeframe. This extinction is considered here to have occurred as a result of increasing changes to surface curvature and elevation of the lands during initiation of Paleozoic geosynclinal and orogenic activity. This orogenic activity deepened the continental seas and progressively drained waters from the shallow coastal shelf areas. It is shown that these changes then disrupted the configuration of previously existing coastlines and the overall distribution of continental seas. Crustal changes in one area during changing surface curvature globally affected coastlines elsewhere by changing the overall global sea levels. It is speculated that these changes in sea levels may have then adversely disrupted favoured continental shelf habitats, as well as disrupting established migration routes, which in turn led to extinction in these regions. The End-Devonian Extinction event occurred over a period of 15 million years at the Devonian to Carboniferous transition. During that time, the previously well-established network of interconnected continental seas was being subjected to ever-increasing adjustments to surface curvature, geosynclinal activity, and orogenesis. On small Earth models, during these times, the ancient continental seas continued to further separate into a number of deep and restricted seaways. The geosynclinal and orogenic activity occurring at that time also provides substance for a series of extinction pulses occurring during this event, as noted by others. This restriction and isolation of the seas again severely disrupted favoured continental shelf habitats and established terrestrial and marine migration routes. All of these changes then adversely affected species development and migration, promoting separate adaptive radiation of species within each of the isolated regions. The End-Permian extinction event was the largest of the 5 major extinctions in Earth's history and occurred around 250 million years ago, lasting for about 30 million years. On small Earth models, this extinction event occurred as a direct result of rupture and breakup of the Pangaean supercontinent to form the modern continents, and draining of the supercontinental seas to form the precursors to the modern oceans. Following this breakup, the post-Permian times are then seen as representing a shift in the style of extinction events occurring on Earth. These events shifted from simple coastline and sea level changes occurring prior to the Permian period to more disruptive sea level changes during catastrophic merging of previously isolated seas and oceans during post-Permian times. On increasing radius Earth models, the End-Triassic extinction event coincided with continental breaching between North America and Australia and merging of the previously separate North and South Pacific Oceans to form a single Pacific Ocean, highlighted here. Here and here. Breaching and merging of these two separate oceans then resulted in drastic changes to global sea levels, such as within the western interior seaway of North America, as the previously separate sea levels equilibrated, which is here and here. These changes in sea levels then disrupted the various habitats and established species migration routes. Merging of these oceans also allowed previously separate marine and terrestrial species to migrate and colonize new habitats, potentially displacing or eliminating less adaptive species. Contrary to the well-known but highly speculative End-Cretaceous meteoric extinction resulting in the demise of the dinosaurs, etc., on small Earth models, this extinction event coincides with breaching and opening of the Southern Ocean, located between Australia and Antarctica some 65 million years ago, shown here and here. The significance of this breaching event is highlighted by further decline in superficial area of the western interior seaway of North America during the late Cretaceous and Paleocene times. The western interior seaway is an important area for dinosaur study and has provided a large amount of data for interpretation of the End-Cretaceous extinction event. These small Earth observations further support the conclusions of paleontologists, where this extinction event was more gradual, resulting from drastic sea level changes already occurring over a period of approximately 8 million years. The following few slides are examples only of an extensive range of global fossil data that's available, as plotted from the International Paleobiology Database in 2015. On each slide, the red dots show the actual site locations of the various highlighted fossil species. During the early Proterozoic, around 2,500 million years ago, the Earth was populated exclusively by single-celled prokaryotic life forms. From these simple beginnings, all advanced life forms later evolved and spread throughout the rest of the Earth. The most conspicuous marine animals with hard parts that evolved around 500 million years ago were the trilobites, as shown on this slide. Trilobites were segmented cockroach-like creatures with multiple body segments and jointed legs that lived in the seas during the early Cambrian to late Permian periods. The trilobites are considered to be one of the earliest complex life forms and are one of the key signature creatures of the Paleozoic era. The distribution of trilobites is shown on the Ordovician model to extend throughout all of the interconnected continental Tethys, Iapetus, and Panthalassus seas, extending from mid-southern to high northern latitudes. Similarly, graptolite distribution is also shown to coincide with distribution of the ancient Tethys, Iapetus, and Panthalassus seas, extending from mid-southern to high northern latitudes. The presence of preservation of graptolites within black shales suggests that the deeper parts of these ancient seas, where black shales are prevalent, were devoid of oxygen and conditions were anoxic. At their peak during the Paleozoic, the shelly brachiopods were among the most abundant filter feeders and reef builders. The distribution of brachiopods is shown on the Ordovician small Earth model to have had an extensive cosmopolitan distribution coinciding with the trilobites and other marine life forms. The brachiopods are shown here to extend throughout the Tethys, Iapetus, and Panthalassus seas from mid-southern to high northern latitudes. After the End-Ordovician Extinction event, broad, relatively shallow Silurian and Devonian continental seas were slowly repopulated and once again teemed with life. The distribution of mid-Paleozoic corals, shown as red dots, along with distributions of mainly marine glacial-related rocks and formations, shown as green dots, is shown here on the Devonian small Earth model. A south polar ice cap located over South Gondwana is also shown as white. No ice cap was present at the North Polar region. During that time, the circulation of warm sea currents around the ancient northern Laurentian supercontinent was disrupted while still retaining circulation within the North Polar region. The presence of corals and other marine species throughout these mid-Paleozoic seas is then inferred to represent a holdover effect from the configuration of earlier seas and also suggests that warm waters were still present. Similarly, the distribution of the glaciogenic rocks in these regions represents elevated mountain glaciers plus glacial-related detritus dropped by melting icebergs within the network of warm continental seas. The late Paleozoic was characterized by profound changes to all life on the land, including evolution of the insects and colonization of broad lowland swamps by spore-bearing plants. Evidence suggests that an algal scum first colonized the land some 1,200 million years ago, but it was not until the Ordovician period, around 450 million years ago, that land plants began to reappear in earnest. By the middle of the Devonian period, most of the features recognized in plants today were present, including roots, leaves, and secondary wood. The general distribution of plant fossils is shown here on the Permian small Earth model. During that time, an ice sheet was present over southern Gondwana, which inhibited plant establishment in this region, and the presence of plants in the higher northern latitudes suggests that temperatures remained moderated in these regions. During the slow recovery from the End-Permian extinction event, a previously obscure group of animals called the archosaurs, a group that includes the dinosaurs and whose living representatives consist of birds and crocodiles, became the most abundant and diverse terrestrial vertebrates during the Triassic. The distribution of archosaurs is shown here on the early Triassic small Earth model at around 200 to 250 million years ago. The archosaurs are featured here to highlight the potential migration routes between the various modern continents, as shown by the green arrows. The first dinosaurs appearing in the late Triassic period were not major components of this fauna. However, by the early Jurassic, the dinosaurs were diversifying rapidly to become dominant occupants of many major terrestrial adaptive environments. While a prolonged period of time involved during this post-Permian crustal breakup era allowed the dinosaur species to migrate to more equitable locations, it also presented new physical and environmental barriers. Draining of the ancient continental seas during crustal breakup, for example, influenced distribution of the modern oceans and hence adversely affected available dinosaur habitats, migration routes, and escape avenues. Migration away from these physical barriers, including apparent migration of the poles, then encouraged the dinosaurs to evolve in new species. In contrast, failing to evolve, migrate, or being landlocked may have also contributed to their localized demise. In summary, it is concluded from this series of podcasts that the extensive, just get this going, that the global data and empirical modeling studies presented here are more than adequately demonstrate that an increasing radius Earth is indeed a viable and demonstrable tectonic process. From a geological perspective, at no point has any fundamental physical law been violated during small Earth modeling. The commonly held presumption that Earth radius has remained constant throughout time was simply removed, and instead the Earth was allowed to tell its own story. In order to create small Earth models, I simply removed from the Earth what was not previously there: intruded seafloor volcanic lava, intruded magma, and eroded sediments, to end up with a Pangean small Earth comprising an assemblage of continental crustal components, and ultimately to a primordial Archaean small Earth comprising an assemblage of equally primitive cratonic and orogenic crustal components. The seafloor mapping shown on the geological map of the world was initially used to accurately constrain the location assemblage of all seafloor crustal plates on smaller radius Earth models. Assemblage of these seafloor crustal plates consistently showed that each plate assembles with a single unique fit, with all plates assembling with a high degree of precision along each of the mid-ocean ridge spreading zones. It was considered that if these crustal plate assemblages were mere coincidence, it would be expected that the seafloor mapping, as well as geological and geographical evidence from adjoining continents, would not match across plate boundaries on any of the small Earth models constructed. The evidence instead shows that seafloor bedrock mapping does indeed match across the plate boundaries. All continental sedimentary basins merge to form a global network of ancient continental seas, orogenic and fold mountain belts coincide, and ancient crustal regions assemble together precisely. What was seen from the small Earth modeling studies is that all remaining continental crusts unite precisely to form a single, complete global Pangean supercontinent crust during the Permian period, at around 50% of the present Earth radius. From this Pangean supercontinental assemblage, continental sedimentary basins were shown to merge to form a global network coinciding with relatively shallow continental seas, and the ancient supercontinents and seas were, in turn, defined by the variation in coastal outlines and sea levels. Quantification of an increasing radius Earth process back to the early Archaean required an extension of the fundamental cumulative sea level seafloor crustal premise to include continental crusts. Continental crust was reconstructed on pre-Triassic small Earth models by considering the primary crustal elements, cratons, origins, and basins. In order to construct these small Earth models, further consideration was given to an increase in Earth's surface area occurring as a result of crustal stretching and extension within an established network of continental sedimentary basins. Moving back in time, this crustal extension was progressively restored to a pre-extension, pre-stretching, or pre-rift configuration by simply removing young sedimentary and intruded magmatic rocks and reducing the surface areas of each of the sedimentary basins in turn, consistent with the empirical data shown on the geological map of the world. During this process, the spatial integrity of all existing ancient cratons and origins was retained until restoration to a pre-orogenic configuration was required. By removing all basin sediments and magmatic rocks, as well as progressively reducing the surface area of the sedimentary basins in turn, an ancient primordial small Earth with a radius of approximately 27% of the present Earth radius was achieved during the Early Archaean, much the same size as the present day. I'll just let that catch up. Okay, so 27% of the present Earth radius was achieved in Early Archaean, as shown, much the same size as the present day Moon. This primordial Earth comprised an assemblage of the most ancient Archean cratons and Proterozoic basement rocks. All other rocks, minerals, and elements were simply returned to their places of origin. From the outcomes of this empirical small Earth modelling exercise, it was concluded that crustal modelling studies more than adequately quantify the validity of an increasing radius Earth tectonic process. What the full range of Archean to present-day small Earth models also demonstrate is that rather than being a random, arbitrary amalgamation, dispersal, amalgamation, cyclical crustal forming process, as we are currently led to believe, crustal development on an increasing radius Earth model is instead shown to be a simple, evolving, and predictable crustal process. In order to quantify the small Earth models created, additional global observational data were presented. When paleomagnetic pole data was plotted on each model, the data was shown to plot as diametrically opposed north and south magnetic pole clusters, as they should do. Each pole location and accompanying equator was then shown to coincide precisely with climate zones established from climate-dependent evidence, such as paleolatitude data and distribution of glacial-related rocks and structures. Coastal geography was shown to define the presence of more restricted continental Panthalassa, Iapetus, and Tethys seas, which represent precursors to the modern Pacific and Atlantic Oceans and emergent Eurasian continents, respectively. Plant and animal species evolution was shown to be intimately related to supercontinental development, the distribution of ancient continental seas, and changes to climate zonation. Extinction events were also shown to be primarily related to and coincident with a number of drastic and prolonged changes to sea levels. However, as you can appreciate, this is not the problem that people see. The fundamental problem that scientists and the general public continue to have is comprehending where did the huge volume of material making up the seafloor crusts and underlying mantle go to when moving back in time in order to reassemble the continents. And more importantly, where does this huge volume of material come from when moving forward in time? A causal mechanism was speculated to be an accumulation of charged electron and proton particulate matter originating from the sun via the solar wind, and recombining to form new matter at the Earth's core mantle boundary. This process gives rise to mantle swell, which is then manifested at surface as crustal extension, currently occurring within all of the modern oceans along the mid-ocean ridge spreading zones. Based on the coincidence of all this modern global observational data, it is fair to then ask the very pertinent question that if this causal mechanism is accepted, as paleomagnetics did for the rejected continental drift theory during the 1950s, do we seriously consider this mechanism, test the new proposal in light of modern global observational data, accept the empirical evidence in support of this proposal, and revise current plate tectonic theory, or do we continue to reject the observational data and acceptable mechanism and instead remain supportive of an outdated plate tectonic theory that insists on a presumed constant radius Earth premise based on a platitude of ad hoc theories? To me, there are too many coincidences within this modern global observational data for expansion tectonics to be due to mere coincidence. It is now up to all of you to consider this coincidence and make up your own minds about whether or not expansion tectonics should be taken seriously. It is concluded here that this data distribution cannot simply be due to mere coincidence and must therefore be fact. Thank you for your interest in expansion tectonics, and for those seeking more information, please contact me at my email address shown on screen.
Oh, I'm muted. Sorry about that. That way I don't make music. But thank you so much. I mean, it really comes down to really what you said in the end. I think what happens with this whole theory, why do people have a problem with it? And it's still sort of that scary idea we're standing on a ball that's expanding. I mean, it's somewhat scary. It's just not something comfortable. I mean, let's face it, emotionally, planet Earth is where we stand, where we live. It's solid ground, we say. And to have the idea that it's expanding, I think is still sort of a shock, even if you have all the evidence. But, and then you were talking about having a mechanism, that's the biggest problem. The truth of the matter is, and what you said, and what is the case with me and many other people, we have often observed things in science, in nature, way ahead of our understanding, right? We don't necessarily have an accepted idea of where the mass comes from, even though we have some really good ideas. I think what you're talking about is probably the closest to what the truth is. So no matter what, even if you think that the idea that mass increase in the Earth is absurd, the data that you see, the continents that you see, the data that you presented is it mere coincidence? It just can't be. You get to the point where you say, I don't care if we have the zero idea of what the mechanism is, because it's obviously pointing to expansion tectonics. We have just loads. I mean, I don't even see, if this was an argument by a court of people from another planet and came in and looked at the evidence for plate tectonics, and the Pangea and all that versus expansion tectonics, I mean, it's not even a contest, in my opinion. I mean, I can't even, if I was giving a task, okay, James, you're going to defend, of course, expansion tectonics. I'm going to go in and I'm going to gather all the information I can to try to support the current plate tectonics. I don't even know where to start. I can't even believe what evidence they would say. And I don't think they do, because you hear silence. I think the biggest shock to me was when you were telling me and us that you really don't go to universities and get degrees in plate tectonics anymore. It's sort of, right? I mean, it isn't there. It's
just accepted. Plate tectonics is not relevant to science. It's just accepted. It's only relevant to academia. It's not relevant to the professions. I've been a professional geologist for 40 plus years and never once used it, never needed it in my entire professional life. and even during my research days, I did not need it. Well, I focused on expansion tectonics, of course, and tried to incorporate plate tectonics, but it just didn't fit. There was no coincidence in plate tectonics. We just accept it because people don't know what it's like. Relativity.
Right, exactly.
We just don't know what it is, so people accept it. People take the so-called experts' advice and recommendations and just accept it. And for somebody like me and us to come along and say, "Hey, this is not quite right. Here's all the evidence," they go, "I don't want to change. I'm quite happy with the status quo." And I we'll just leave it up to the experts. The experts, they have multi-$100,000 grants for research studies to research plate tectonics and to adapt plate tectonics to the data that they're seeing and observing. They're not going to compromise the dollar value, that dollar figure from research. If somebody comes along and offers me a number of $1 million for research into expansion tectonics, well, then I will certainly run with it.
We're working on it, James. We're working on it. What we need is to have a rich person come in, and that always helps. A patron. How many patrons throughout history, right? All the great scientists, all the great artists, all the great musicians. If it wasn't for the people with the money. Here's a really great question, of course, that people have. James Lambert, he says, "What is your response to suggested evidence for subduction?"
Is he going to talk, or will I just talk?
No. The idea here, that's I grab these. The software allows me to grab people's comments, throw them up there with their picture. So this is a comment made.
To suggested evidence for subduction.
Yes.
In my book, I deal with this. There's a whole chapter on. And I don't call it subduction. I call it crustal interaction. The difference between subduction and obduction is the subduction is where the oceanic crustal plates is forced underneath the continental crust. Obduction is where the continental crust overrides oceanic crust. And this, if I can just get back to my hand, get it right now, with changing surface curvature, you get a flattening over time. You start off with a smaller radius Earth, a tighter surface curvature, and over time the radius increases, but all the surface curvature flattens. So this is where your interaction zone. So you're actually, get this way. So you're actually interacting at this point. So that's where all your subduction related data is coming from, but it's just the interpretation of this data. Apart from myself, nobody else has bothered to reinterpret this data, the subduction related data, in any other context than plate tectonics. So hence this, myself is constantly bombarded with this this so-called evidence about subduction, but it is only purely local. It is a crustal interaction at that major boundary between continental and oceanic crustal plates.
Yeah, and is this interesting? I don't know. Did you get a chance to look at that one video we put? Someone found it was making its rounds on Facebook, which is this guy. I think it's called See the Pattern or something like that. And in that, he actually looks at subduction and makes an argument against subduction. That what they, I guess he was showing some. I'm going to see if I can find it. Here we go. I found it. Let's see if I can get to that. And he actually names you in the your name's mentioned in a good way. So let me see if I can get to that part. He talks about subduction. I think that would be good for us to take a look at it because he has these plots, and I was really interested in looking at that. So I'm going to sort of play this. Let's see if I can show this here. I'm going to stop your share. Can you stop your sharing there? Because I want to share this. I think this will be really quite interesting. There we go. I can share my screen. And I'll share that with the audio. And let's play this because I thought it was really interesting when I saw this guy. Here's a guy, again, see the pattern. I'm going to show everybody here. It's called See the Pattern. And he's made numbers of, he's just sort of a critical thinker. And he just goes out there and finds something interesting. But he talks about the subduction, and he shows some really interesting parts of that subduction. So I'm going to go ahead and play this.
Both at odds with the concept of subduction put forward by plate tectonics. The main differences come down to how far down this subduction continues. Plate tectonics would have this going on for thousands of kilometers, which, as we have discussed in the episode What Drives the Plate Movements, cannot really occur. Recent high-resolution global mantle tomographic models provide images of subduction zones very different from the expected ones. The narrow high-velocity zones under the Asiatic Circum-Pacific arcs appear not to be prolonged towards the lower mantle, but instead deflect horizontally into or under the 400 to 700 kilometer transition zone, and a horizontal flow must be admitted. In some cases, it even appears as if the leading edge has an upward motion. This presents a problem for the normal plate tectonics. As the plates reach a depth of 700 kilometers, its own decreasing buoyancy should pull the rest of the plate with it and plunge it towards the mantle. But here we are seeing something very different. The motion is not downwards, in some cases it is even upwards. Experiments conducted with different kinds of slabs show that stiff slabs tend to curl like wood shavings, and weak slabs tend to undergo retrograde subduction, none of which fit with the standard tectonics model. High-resolution images of the mantle plumes under the major hotspots show that the plumes can be followed up to at least 800 kilometers in a nearly vertical manner. With little to no deviation, this strongly suggests that there can be no convective circulation processes going on. Number 2. Distortions in the reconstruction of Pangaea.
Okay, so what did you think about that?
That actual, I think I've used that image, that first image in my book. I think, whether that's the third book or the second book, I'm not too sure of, but I think I have used that. I'll just, that's a cartoon, by the way, that image. I'll just get back to my my crust, my increasing crust, my flattening crust. In my book, the way I analyze this, I'll try to get it in perspective. We have a vertical crustal component. As the crust is flattening, we have a vertical component. Think of this as vectors. We have a vertical crustal component, and we also have a horizontal crustal component the other way. So we have a vertical and a horizontal crustal component. Give you the screen again. And then we also have a third upwards. The sum of those two, I'm not very good at this. Some of those two vectors is the other way. We should get my book out and show you this. I'm trying to show you an upward vector and a horizontal vector, and the sum of those two vectors is that way, which is subduction, or in my case, obduction, where it's an upward moving motion. And as I say, I deal with this whole chapter in my book about crustal interaction, as I call it.
Okay, here's another comment. Subduction is an illusion created by the redistribution of material out from under continents to feed the newly forming ocean floors. Is that what you would consider to be subduction?
Well, subduction.
I mean, by their terms.
It's an ad hoc theory. It's an ad hoc theory which needed to be created to what's the word, to
counteract the expansion.
counteract the new material coming up
right.
through the mid-ocean ridge.
So it's really a relatively new concept, really, in geology.
It had to be created right in the 60s. It had to be created in the 60s,
right?
Because they recognised seafloor spreading at the mid-ocean ridges. Then they had to explain where it goes to. How do you dispose? You're creating new oceanic crust. You're creating new material. Each of these things is opening up between 1 and 14 centimeters per year within these mid-ocean ridge zones, spreading zones, and you have to then maintain a constant radius Earth, constant surface area Earth. You have to come up with an ad hoc theory to explain where it goes to, and it's just built on over the years, over the decades. It's built up and up and up, and this is a so-called proven science now, subduction. But they just haven't utilised the same data as I have. What I've done is utilise the same data and explain it from a different perspective.
Right. Now I know we're repeating here a little bit, but I'd like to answer some of the questions because there are people who have come in later. They haven't seen all the, this is obviously one of the common questions. Where does all the water come from? There's not enough in rock, but you're saying really the water, there's quite a lot of water in the mantle itself, right? Within the rock. Yeah, can you explain that? Again, I know you've done this, but we're trying to answer questions here.
What people don't appreciate is that the seafloor crust, the oceanic crustal material, is exposed, quenched, and exposed mantle. That they're mantle rocks. So the continents are continental rocks, the continental crusts, and the ocean seafloor crusts are actually exposed mantle, quenched and exposed mantle. Volcanic rocks, in particular, your denser rocks like basalts, etc., have between, I think, 15 to 20% by volume of fluids and gases in their crystal lattice. This material, this new material which is being intruded along the mid-ocean ridge zones is coming from the mantle. It's being intruded from the mantle, and this material, once it reaches the surface, it devolatilizes, and this material devolatilizes out from these volcanic rocks, and the what do we call them? The black smokers along the spreading mid-ocean ridges. They're a classic example where there's water and gases pouring into the new ocean. So you can't just say, where does all this water come from? It is coming from. We just have to refocus and look at it from a different perspective. We have water coming in all the time. It is increasing the volume of the ocean waters.
Yeah, I've said this often.
And I did a quick calculation.
Sure. The
volume of the oceanic crusts. You can do a quick calculation. So 15 to 20% by volume of that roughly equals the volume of the seawater. So you can do a back calculations and you can get pretty close.
Right. I mean, it's you get a lot when you go to when you're in high school or you're in university. Basically, what you hear from them is it maybe came from comets, but it doesn't explain enough, right? So, I mean,
if it came from comets or anything like that, it would be recorded in geology. Geology is like a book. It's a book. You can read every event on Earth. You can read in the rocks. If there was a catastrophic event such as an ice comet, you would see it in the rock record. You would see an instantaneous extinction event, worldwide extinction event, and it'd be more catastrophic than what we see in the opening of the seas.
Right. Here's a question we're getting a lot, actually. Where can I buy your book? I can't find any place selling it. Where can we get that book now? Have you checked it recently? I know it's been not problematic, but it's been difficult for some places on the continent.
I'm having trouble with my publisher. What I'm doing at the moment is getting it republished through Amazon. So it will be available through Amazon shortly.
Oh, okay. Is that going to be in the UK and the United States and Australia?
Globally. and it's with them at the moment. The manuscript is with them at the moment, and they're processing it, reformatting it to get to that.
Yes.
So you just with me at that time, and I'll make an announcement.
Okay, that'll be great. No, we'll announce it here too when that happens. Maybe we can, once you get it out and people are buying, maybe you can have you back and you can literally talk about your book. What's in the book. Okay. And this is something that sort of hit me, and it actually, when you were talking, you actually said this, because I don't know why this hit me all of a sudden. I've been a student of how do you say, expansion tectonics and yours for quite a while, is that it was it was what epoch the moon and the earth were the same size?
Early Archaean.
Okay. Now, if you look at that in physics, right, you have two bodies that are now more the same size. And normally when you have orbits like that, you're going to have, one's going to be a little bit more in the center, but you certainly have a lot of difference going on. Right now, of course, the Earth and the Moon, when they go around each other, the Earth's not staying still. It's going, it's also wobbling, right? Because this is part of, basic Newtonian physics. So have you looked into that? Because I was thinking to myself, if we know this, maybe there is some way we could even go back in time, looking at the orbit now, our positions, move the size back. The moon is expanding very little, if at all, right? Then is that the case, that you would say that the moon and the Earth were pretty much near the same size at one time?
Yes, during the Early Archaean. I've tried numerous times to do that, but I'm a rock licker. I'm not a physicist.
So that's a good project for someone to do then.
So it has eluded me. And I didn't. I introduced that concept in my third podcast,
right?
But I didn't delve deeper into that. In my book, I delve a little bit deeper and suggest that the Earth Moon system, Earth Moon, and all of the planets, the solar planets, originated from the sun. So, in order to do your maths, do your physics on the mechanisms and physics behind the astrophysics behind what your question was, you also have to vary the solar radius, the Earth's solar radius, with time as well. So that's where it becomes complicated. Okay. And I wasn't capable of doing that.
Right.
Tried very hard. I was not capable of doing that. So that is just what are they called? The sunspot activity on the sun now, where you get mass ejection of plasma material from the sun. You can envisage that in the primitive young sun stage, where you are flinging off planet-sized bodies of incandescent glub, however you people call it, and that beyond the influence of the young sun, that material then goes into circular orbit around the sun, and over time it gradually cools down, and you're changing orbital parameters. You just migrate away from that particular planet, migrates away from the sun, and then it happens again and again and again. With the Earth Moon system, I envisage it being a destabilized, like they were joined together, of course, they were one body, but an unstable body, an unstable rotation, if you get my drift.
Right, yeah.
And then over time, that gravitational instability then enabled them to separate and form two bodies.
Right. Well, I think part of it too, you said, was really the density, right? Because what sloughed off wasn't the same thing. It wasn't like, here's an orange, I'm going to cut it in half, and now you have two oranges. It was very different composites, right? Compositorily.
Yeah. It's like having an orange and covering it with cream.
Right.
And then spinning it, the cream will fling off,
Right.
leaving with the orange. So the orange mantle core, whereas the cream crust has been flung off, so that becomes your moon, and the rest remains as your Earth.
Right. Right.
Completely
Okay.
separate.
Here's another one. What about the north-south spreading in the Atlantic? The cracks run both ways, unless you covered that already. I just got here. That's okay. We're going to ask questions. Obviously, we know we've had 4 talks, and some of them been answered. But I think it's good to get people's. We got him here. Let's ask the professor. So, do you get that question? What about the north spreading? Yeah.
I'm not 100% sure what the concept is, but I'll just. If you can move that away, I'll just do a hand demonstration. When with Pangaea at 50% of the present Earth radius, all of the continents were joined together, and then during the Triassic, the Pacific Ocean started opening up, and then the Atlantic and Indian Oceans, and then the Southern Oceans, and then and as well as the Arctic Ocean. So there was an asymmetric opening and increasing radius. So I'm not too sure what the context of the question is, but I think that's the context where you're getting an asymmetric opening and opening of each of these oceans. And it wasn't all together. The Pacific Ocean, North and South Pacific Oceans opened first, and then the Atlantic and Indian Oceans, and lastly the Southern Ocean, as well as the Arctic Ocean, and then the Southern Ocean opened up in the Paleocene. So I think
Okay. All right. Here's another. Let's see. Oops. There we go. So water creation will be happening in a diminishing degree through the full life of an expanding planet.
No, that's incorrect. It'll be an increasing degree because you increase material that's coming out of the increasing surface area, increasing volume, increasing the quantity of material coming out of the mid-ocean ridge cracks.
So that's also then meaning our shorelines will get. I mean, the water depth will get. Is actually going faster than the spreading, meaning it's not a 1-to-1 correspond. That'd be awfully, how do you say, coincidental if the expansion worked exactly so that the water would stay pretty stable. But it's been pretty stable in some sense, hasn't it?
There's a complication there in that when you have the flattening of the surface curvature, that's affecting the sea level. So if you got the sea level here, if your sea level's here and then you're flattening it, then your sea level's moving away, moving down. So you're exposing your land. Whereas up here, where the surface curvature is different, it's quite high. We have, I could explain it here in Perth, Western Australia, where we have a range of hills at that higher level, and then over time that sea level has decreased for about 20, 30 kilometres away from that range of hills onto the ocean now. But the complication is some continents are stable, so the sea level is changing because of global sea level changes, and other areas the sea levels the apparent sea level is receding, moving away from the continent, and that's because of the flattening of the surface curvature. So I think I quoted an example last presentation in that figures quoted for Sydney, say, for instance, in New South Wales, are different. The rate of change of sea level in Sydney is different to the rate of change in sea level in Cairns, which is another.
So it depends on more than obviously just water coming in. You've got expansion going on. Expansion is not equal everywhere. Upheaval is not equal everywhere. It's a mess.
The climate scientists have us sort of have us convinced that it's
right.
That changing the continents are constant and it's the sea levels are changing. That's totally incorrect. It's the continents and the sea levels, they're moving up and down all the time. In general, the sea levels are actually lowering.
Okay. Yeah. Okay. Right. Okay. Here's another one we've already covered. This is actually from a private chat, so I'm going to put it up there. But again, I want to answer if you have questions. Yes, we've been here and he's talked 4 times. We're repeating ourselves, but we do want to answer questions because we have new people all the time. So this is a common question. Why would the Earth expand but not the moon? We've had that before. Can you re-explain that again?
Well, yeah, we dealt with it a moment ago in that it's in expansion tectonics, the moon is the crust. There's the ancient crust which has been stripped off, which is equivalent to the oceanic crust, basaltic material from the that's making up the oceanic crust. So if you strip off the oceanic crust, that crust is already dead crust, so it can't expand anymore. Whereas the Earth, the proto-Earth, the ancient Earth, comprised the ancient core and mantle. So that's where the complication comes into it. That's where your magnetic body comes in, a spherical magnetic body, and that's the one that's sucking in this particulate matter from the solar wind. That's the one that's increasing size. In size, the moon essentially has a very weak magnetic field, and it's not sucking in this material because
if it is, it's very small. It'd be more probably like the Earth in its early days, right? Not really happening. Right. So, okay. I had another question. Today we live in what epoch do we live? Epoch today. What do we call it?
Hadean. No, not Hadean. Yes, it's a good question.
Ooh, stump the professor.
Anthropological or something like that. It's to do with
humans.
Yeah,
we had to insert ourselves in there, I guess.
In geology, it's called the Holocene, which is the past 10,000 years. So I would include Holocene, everything in the Holocene.
Yeah, I mean, because if you look at epochs, what are the major reasons for their distinction? Are the extinction events? Was it just somebody who came up with it? I mean, no. How are those things decided? I mean, are we in the beginning one, or are we just making it up as we go? How do we do that?
No, it encompasses major events in the geological rock record, and extinction events is one of the ones that create boundaries. Major changes in sea level will influence sedimentation, deposition of sediments, which can be more prominent, say Britain, England, say for example. That Britain and Europe, that's where most of these the periods were developed, and they were based on characteristic rock records separated by major disruptions to that event. So you get packages of what's it called? I'm having a seizure moment. Yeah, you have packages of sedimentary strata, then an unconformity. That's the word. An unconformity or disconformity, more sediment above that, another disconformity, and more sediment above that. So that represents, say, 3 periods, and then your eras are generally they encompass those events. So your Paleozoic starts when the fossils, when hard bodied fossils first developed, and that encompasses right up to when the continental crust broke up, coincidentally as it did, broke up and separated to form the modern continents and oceans. And then the Mesozoic encompasses the breakup of the continents and opening of the oceans, and then separation of opening up of the Pacific Ocean used to be two oceans, and then break up and merging of those two oceans, that represented another era, and then the Cenozoic era is up to the present day, and then within those eras you have these periods and epochs within that, and encompassing the whole lot you have eras and eons and eons that encompass those. So it's quite complicated.
Well, look at here. I mean, for those who don't know, I'm in Boca Raton, Florida, which is a wonderfully comfortable 11:30 in the morning, more or less 11:24 in the morning. And James is in Perth, which is now past midnight. He's already into Sunday, right? You are 24 minutes into Sunday. And for being a senior, you're in pretty darn good shape because most of the time, most of your senior friends are napping as they should be, but you're here with us. So it is nice to see that you get comments like this. So glad I was awake to catch you guys doing this morning. Now, what time frame he's in, I don't know either. So, but again, I always blame the time zone problems on you, James, because you
remote. That's why I'm so remote.
Yeah, exactly. We would be in a much better shape if we, believed that the Earth didn't expand and for some reason all that stuff really didn't move around. We would be a neighbor to you, actually. So, but actually, this is an interesting question. If we were to go back in time when we're all, when the cracks, the crusts were all to break up, Australia is really bordering on almost everywhere in some sense, right?
From Brisbane, where I used to live, I could have walked to your old place in Los Angeles.
There you go. And then on the west side, you're that at the 250 million years ago. What's the west side where Perth is? What was that butting up against?
Korea, China.
So there you go. That would have been, man, you guys would have been in great shape because you would then been able to build all these railroads to ship stuff across instead of the ocean. You guys would be just, everyone, you would only be a stop between two other continents. So I don't know, but it's always interesting to me when I remember when I stood learned about expansion tectonics and I went out to the Pacific Ocean when I lived in California and I looked out and go, that is really bizarre. This whole thing wasn't here. It's just, it is quite shocking to find out. Okay, I see Bob Gray, and I know he's raising his hand, and we do have people in the green room. We're coming up to about a half an hour. I do see other people in there. I know Bill wants to come in. I'll talk about, I know what Bill wants to talk about, but let's get Bob Gray in here and say hello and see what he has to say. Hey, Bob, how are you?
Fine. Thanks very much, James, for the presentation. Do you have your data in a GIS software or other form? I don't know if you have any of this available. If you're making this, if it's in a GIS.
The short answer, Bob, is no.
Okay.
And the long answer is we're working on getting it into GIS. It's a very
excellent.
Very, very complicated process, as I hope you can appreciate, because it's as well as dealing from a spherical format to, say, a Mercator format, a flat map format. We're also changing in size as well. My early modeling, I got most of them in. I used to use MapInfo. I don't know if you have that over in the States, but I used to use MapInfo. And from MapInfo, you can then migrate that, sinusoidal format that I used into my present-day map. We digitized that, and that's in digital format. So the primary base map that I used, and that's in sinusoidal format. And we were able to migrate that directly into Google Earth. So I was able to drape it into Google Earth, and I've sent a copy of that to David.
Yeah, I'm curious to know if you've ever found any GIS software that has a radius parameter.
No, I haven't.
No.
And
it's
yeah.
Well, speaking of that, I will speak to that because I actually did this. I'm going to share my screen again here with everybody. If you look here, what I did here, this is the Google and their Earth Enterprise, which is the software for Google Earth. Now, it's open source. So I put this in there 8 days ago, and I've gotten 0 crickets, nothing. Here I talk about look to fork Google Earth to be able to change the Earth's radius and overlay with time. So let me see if I can increase the size here a little bit. What I put here, we are a group of geologists, scientists, engineers, computer programmers who are looking to fork Google Earth software to modify it in order to be able to change the Earth's radius with time and to be able to plot flora and fauna and geological information on it. For example, 200 million years ago, the Earth's diameter was about half the size. What we wanted to be able to change time on the model, therefore radius and its overlays. This would allow scientists, blah, 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 blah. We know what that would allow. And of course, I'm wanting to guidance on this. And of course, I'm asking, is it possible? Is it hard? Can the overlay database be easily modified? I mean, all basically you would have to do, let's just put it this way. There's plotting, Bob, there's plotting of information. That plotting has geological coordinates, correct? Well, all you have to do in the database is put one more column in the database. Right. Basically, you put a column and you put time, and maybe it would be in millions of years. You would do it in millions of years because whatever the time increment would be. So yeah, everything in there right now would be all labeled, current, and put in the time there. And maybe we would just go millions of years back. So if it's 2, 3, 4, 5 in that column, then what would happen is when you would look at Google Earth, you would just have literally a little type-in box or a pull-down box where you could type it in and the Earth would go down. Now, the only thing we would have to do would be able to not only do the overlay, we'd have to do overlays for the continents themselves, right?
Okay. I'd like to suggest looking for software that they use for the planets. I know they map out, of course, the moon, Mars, etc. These all have different radii.
Right.
So there's got to be some software, GIS type software out there someplace that would allow you to do exactly what you're saying, David. Just call it a different planet rather than Earth with a different radius.
Right. But I think, I know what you're saying, but I think what really is happening, and if I understand it right, you can actually, even in Google Earth and in any of these programs you're talking about, what they do is they basically have a format of a GIF or a PNG file, a graphic file. And that graphic file has to be of a certain format. How do you say it? How the resolution, of course, it matters, sure, but you can probably have it at most any resolution. And then they have all these programs have a draping function. So you would take like James's his models, put them onto one of those, where you see a rectangle of the surface of a spherical body, which of course is distorted mostly at the bottom and the top. But then they have programs that literally will overlay that. Now the difference, I know what you're saying, but I think the difference would be what I would like to see, no matter what software would be the ability to plot on it and then to change it and have that change. Because right now what you can do, of course, is what we would do is to take every one of James's models, make a rectangular,
Mercator projection.
Right, exactly. Okay, that type of projection for each of his models that he has, and then we can drape it over. And of course, you can then make them different shapes, different sizes. I'm sorry. The thing though, what would be really good is like a Google Earth, so that someone could go in, change it to 10 million years ago, and start plotting their information right there. And that plot will be put there, and that plot then could, there's all kinds of things you can do with that. It would just be then if you go a million years after that plot's not there. Or if as you get bigger, you have to have algorithms, obviously, that will expand that, right? So that if you plot it in this one point, as you go further in time, you're going to try to keep where that is. But that's even tricky too, because I know James knows this very well, and he talks about it. It's not just a uniform, you can't go 250 million years back, put on the continents, and then just let mathematics take over. It's sort of messier than that, right, James?
Right. Yeah.
So I guess what we can do, Bob, I'll let you speak, but I want to make sure we did start a sort of discussion on our website. We need to discuss this. So go ahead, James. Go ahead. Bob. I'm sorry. Go ahead, Bob. You want to say something?
I'm done for now. Thanks again, James. I really appreciate you staying up and doing your presentation for us today. Thanks.
Yeah. I mean, it's really great, James, that there is interest, and I think if we make ourselves a little, try to keep the discussion going, looking at all the software, like Bob was saying, trying to find those things, because I mean, I think it's. I guess what I want to say to you is, me as a software engineer, because that's what I do all my life. I just would rather try to do it in a way we know that will be useful in the future, because one of the things is if you make all those projections that you were talking about, and we put them on, drape them over Google, I mean, that's great, but it's not changing. And I think one of the interesting things about trying to make, I think. Right. And I think what would make this so monumental is not just simply, here's this and we'll plot stuff on it, here's this, is to actually be able to go back and forth and be able to look at those things and compare those things, because it's in the dynamics and the changing. And if we get software to do that, then you would go in there and you would just start plotting what you have on your maps, right? And we would plot them in ways, for instance, basically the software would say, it's very simple. The database isn't very mysterious when it comes to the actual objects. You have line segments, and you basically make little line segments, around all on your models, which on these models, you have all these different colors. Well, all these colors, if you look at any of the continents here, let me get to a continent, which would be Australia. So if you get to Australia there, you see Australia isn't all one color, and every one of those areas that you see there can be plotted. You would basically have this in your hand, go to the Earth, Google Earth that has expansion, and at this time, whatever epoch you would be in, you would plot those things. And then you could label it, and you would call that a certain plot a label. And then when you would go to your next model further on, you would then be able to, this is this at this epoch, this is this at S epoch, same label. And then when you do the expansion part, you can have mathematics tween them. I don't know if you know what tweening is. It comes from the word between, and then it would be able to move those things. So yeah, I mean, the idea would be, ideally, instead of draping graphics over it, I mean, you could do that. Ideally, you would drape graphics over at this radius, go in and then plot them, right? Make the plots so that those become algorithmic and not simply an overlay. So then you could go in between places that your models, right? Because your models take a long time. We're going to say, if we're going to make this into a lot of feature-length film, we would need 1.3 million of your models and to get all the changes. So I envision us trying to find software to do something like that. So I think that's interesting.
What Bob brought up, though, they must have something available for the other planets.
Well, I'm a software guy, and this is what I think is really happening there. What they have is they have ability to plot something on a sphere. What you then, as my software, I can make that any scale I want, right? You don't have to change the internals there. The internals to drape this over a something, and they have, of course, a ways to go in and out from that. But what they don't have internally is something that actually in the database that would change with the time. It's not there. So what they do is they'll just say, okay, I'm draping it over this. Then they have a scale. Okay, what's the scale in this one? Okay, the scale is this. Its radius is this. And then, then they can plot that next to other things. But what they don't have is you say, oh, here's the Earth, and I need the same thing, but I need 1 million years ago. And what can I have plotted on that? So even though they do it, it would be the same thing is basically, like I'm saying, you can go to any of these, including Google Earth, put your wraps around them. And you can, who cares what you think the size, just change the scale that I'm displaying for you, right?
Yeah, I know what you're talking about because I have done that in Google Earth
Right.
with about 4, 5 or 6 of my earlier maps.
Right.
And yes, they just drape straight over Google Earth,
Right.
At that pre-existing radius. It's just that and then what you say, you readjust the scale of your image or whatever you do.
Yeah, I mean, they can do that. They can zoom in and out. But what people have to understand, software-wise, they're not making any changes to the internals of that. What they're doing is they're simply have algorithms of drawing it on your screen. So when you say it's zooming in, all they're doing is they're now redrawing the whole thing at a different scale. Right? And they have a process to do this. That's very different from actually having the software saying, not only do I do that, but I'm going to plot it versus time. There's never been a reason for that. There just hasn't. And again, the modification isn't that hard because just like you have a scale, right? And they change the scale for this. Okay, now it's Ganymede, so we're going to put drape it across for our graphics. When they do computer graphics for the Discovery Channel or the Science Channel, they do that, and then they just drape it over that. It's just a matter of literally what you see, but they don't have it so that you can say, oh, I want Ganymede, 5 million years ago. It's a whole different plot. Okay, but it's not that hard. It just means you're going to have lots more data because you're going to. But anyways,
I'll give you the formula for it anyway.
Yeah, no, I got that. I got that formula. I know where that formula. I haven't memorized it though, but.
What you should have done with that graph there, you should have done the one from my book where I have actually got the formula on the graph.
Yes, you do.
Yeah.
And again, it's just I need to take a look at it myself. What we need to do is find some software people that are interested, because if we get software people interested, then we can start modifying it and taking a look at that. The other way to do that too is to raise money for it. I mean, it sounds crazy, but you can get programmers to do anything if you have some money, and you can create a real project. And if you have very clear, just like Jeff Yee is doing his energy wave theory, and he put up $15,000 to have people do programming for him. So all we need to do, but you can do this on Patreon. If you get everybody giving $50 and you get a bunch of people to do that, you'll have enough money for somebody to take Google Earth and fork it and then start making the modifications necessary. So that's just another way you can go about it. So. All right, I know Bill Lucas wants to talk about expansion his idea of how expansion can happen in the physics level. I mean, I'm going to say that more near to the end because that's really more just going to be a discourse of what he thinks is happening. I'm not sure it's going to be much of a how do you say? I'll save that more to the end. James Keene, you're around in the room. Did you want to come up and say anything, or you just wave off, or no, yes? Okay. Let me see if I can add him. James Keene, I want to thank.
Hi.
Yes, go ahead.
Actually, thank you, James, for your wonderful work and presentation. I have so many questions. Like for one thing, wouldn't the average radius of the Earth's orbit tend to decrease around the sun? I mean, tend to decrease as the mass of the Earth increased over this time.
Well,
that's question one.
As I pointed out, I'm not an astrophysicist. I maintained it. Well, it must increase, but there must be some way to work the maths out. I'm not a physicist.
Well, I can say I will jump in here a little bit on what my mentor, Dr. Wait, hold on, just a second. I just do want to make a comment on that. My mentor, Dr. Riccardo Carrizzani, who showed Einstein wrong. One of the things he did believe was mass increase. He didn't really, we never talked about it. I met him in the early 1990s. We didn't have any idea that expansion tectonics even was out there. And he had talked about mass increase. And that's the reason you have these perihelion advances for those people who know that. That's basically the perihelion of orbits change. And they claimed that relativity explained that. Well, it turns out it doesn't. And the pioneer slowdown. So one of the things is the moon going away from the Earth and the orbits going further away from each other. At least from these physicists, their calculations was that it actually gets further away, not closer. So, okay, I just thought I'd step in there. Go ahead. I'm sorry to interrupt, but I was part of the...
Well,
Go ahead, James.
Wouldn't that,
Keen.
what David just said, contradict Newton's universal gravitation? Like if the mass of the Earth is increasing, wouldn't it tend to move closer to the sun?
I shouldn't think so. I'm not a physicist, but I shouldn't think so.
I think it depends. Well, I think that's a really good question. I'm not going to, say I'm going to have the answer for that if that's, what that answer is. But it is one of those areas, James Keen, that we need to look into to understand everything. Just like the same thing. My question is, and what James says, he doesn't have the maths to do that, or he's doing too much already, anyways. But what was the Earth orbit like when it was about the same size as the moon? So yeah, that is a question. Is that in conflict? From what I have heard, no. But again, I don't have anything to back that up, and that's something we need to look into for sure.
Okay, well, one of the fine things about James Maxlow's work is good work in science raises a lot of new questions, and so my questions are not intended to cast any aspersion.
No.
It's more to congratulate him on his work. Like, for example, the question comes to my mind, not being a real professional astronomer, is well, how about other planets like Venus and Mars? Are they expanding also? Or that's just another question that comes to mind.
Yeah. Well, as I pointed out in my last presentation, the giant planets, the Jupiter, Saturn, Neptune, they have extremely high magnetism on those ones, whereas the inner rocky planets are essentially zero to very, very low magnetism. And that it's the giant planets are expanding. It's not the inner rocky planets. So, to me, the Earth is in a transition stage, transitional between the size of the inner rocky planets, and the giant planets. And as I pointed out early on, within 500 million years, the radius of the Earth will be of the order of the giant planets. So yeah, the giant planets are giant planets because they're sucking in these particulate matter as well as the Earth.
Okay, you mentioned last point, if I may, you mentioned sucking in particulate matter, and you mentioned protons and electrons, for example, by the magnetic field effect. It occurs to me that, well, in my work, basic energy quanta can be assembled into these formed, what I would call formed particles like electrons and protons, meaning the relevance being here that all of the light or the electromagnetic radiation, not necessarily just formed particles in the solar wind or whatever, all of that energy is coming to all of these planets, including our own. And with baryogenesis, that energy can be assembled into protons so that you don't have to say, oh, well, there's a proton in the solar wind and we capture it. Just any electromagnetic radiation, the energy that it carries delivered to Earth could increase its mass. And that would be a very interesting calculation to do in terms of the billions of years, the amount of solar energy arriving in the form of electromagnetic radiation, in other words, light and heat and so forth. Does that quantitatively add up to the amount of mass needed to expand the size of the Earth? I guess that's not exactly a question, Doctor, but just a comment, and I'll conclude there with that thought, that it would seem that the work that I've done with regard to baryogenesis actually could further support your model.
Good.
Thank you for your attention.
Yeah. I can't answer your questions because, again, I'm not an astrophysicist or anything, but I would refer you to John Eichler, who I would suggest we get him on for a talk there, David, sometime.
Yeah, no, absolutely. What I'd like you to do is maybe, because one of the reasons is this group is chomping at the bit to have their versions of what mass increase, where that could come from, and that is actually a very valid question. And what I'm thinking is, I know Bill Lucas is here; he has his answer. Lots of people in physics have already talked about. My mentor had no idea that expansion tectonics existed, and talked about mass increasing causing the moon to get further and further from the Earth because whatever. So I think one of the things we could do is maybe you can send me if he can talk. I think we can then maybe shift to a more specifically focused discussion on the expansion part and the possible mechanisms that people would be proposing for that. I think the most.
He gave a talk last week with Stephen. Did you?
No, I didn't see that. No, I did not see that, but I did hear about it. Yeah. So I think what you want to do is once you guys talk it over, and I'd love to have him on, and we'll have him talk about that, and then maybe what we can do is make a focus for 1 or 2 weeks on people's proposals for what expansion could be.
David, is he online? Is he logged in?
I don't think so. I didn't see him, but it doesn't mean he's not here. But it is the Thanksgiving weekend here in the States, so people are traveling not as much as they would with COVID. But I think that's one of the things we could do is to actually make a segment for that, because again, I think the way I look at it, James, is that like I remember maybe 10 years ago or something, you sort of yelled out to us saying, help me, I know mass is increasing. I don't know what mechanisms that could be. You've also then went on that journey yourself. And I think the basic, how do you say, consensus, there is a consensus. And that consensus is the mass increase isn't from accretion at the atomic or molecular level. I think that seems to be a consensus, that the mass itself is coming from a subatomic world. Now where? We don't know. It's the putting together of atoms or adding to atoms that are already there to make them larger, atomic structures, whatever. I think that seems to be a very common theme. I think people realize very quickly that just all having coming from, dust settling on the Earth all the time. So, I mean, I think, yeah, exactly. I think that seems to be the consensus. Now, what we don't know is really what that process is. And I think there are some clues, and those are some of the things you've talked about, which is magnetic fields. And again, really comes down to, James, you have to know, what is a magnetic field? We just talk about these things. What is really an electron? Is it an electron? Does it have charge, really? What is charge, really? Those kinds of questions, of course, are a very more focused, more specific question. So let me ask you, because we're getting close to the time. We've got about 7 minutes left. So what is next for, other than the university? Or maybe that's next. I really do see a need for you until you get your, I would love to have Dave. I wanted to, help out and write some courses for the online Natural Philosophy University, but Princeton is called, and I'm now going to be a professor there and teach expansion tectonics. Probably not going to happen, unfortunately. So what are your plans for the future? Are you working on another book? Would you like to concentrate on the teaching part? What are your plans?
Yeah, I'm just waiting for you to give me a format and a go, and where to and how to or what to. And as you know, I'm retired now, so I have more than enough time up my sleeve. But I also have to get back to my models, and got my models. I hope your viewers there appreciate. My models are hard copies.
You have no idea how hard it is to make these.
Here's one.
Yeah, people
Here's
have
one.
no. In fact, if you get the book, your book, which everybody, again, it's coming out in. I'll show you this, people. This is coming out on Amazon. He's promising that worldwide. Now, if you look at this bottom part, I love it. In fact, I will tell you, James, I like this sort of format of the white and the little thing wrapping around like this so much. If you see my dad's cover of our book and it looks somewhat similar, please don't chastise us. Remember, copying is the biggest form of flattery. But I redesigned our cover and I like this so much, I said, I'm going to use it. But if you look in the bottom here, this is what really goes into making this, right?
That's called a gore. Each one of those is a gore. That's
A gore. Oh, wow.
It's a 24 gore sinusoidal projection.
Oh my gosh.
You cut each of those gores out and you can glue it straight onto your
And that takes only, you can do that in 5 minutes. Not, but you must have, I mean, do you buy these commercial size styrofoam, right?
That is, yes.
Okay, and you get them in centimeters, obviously, because you guys are smart like us. I'm not like us, that you have a metric system. And so you must have like this all, I mean, what did you do? Since we do have a little bit of time, how did you get to this part? Obviously, they're graphics, but did you draw them? What did you use to draw them? Because I'm an artist and
the first models I made, I had the foam cut to size, so it's the same. Each of the models the same scale, and you visualize an orange. You unwrap the orange. Where are we going? You unwrap the orange, and you have a series of orange segments like so.
Right.
And then what it comes as a big rectangular chunk of polystyrene, and what that's called is a comb. So you then take out these wedges between the combs, and then they all join together to form an orange-shaped globe. The problem I was having is getting them millimeter accurate, and then you draw. My first ones were hand painted by my wife. Wow. But then I was having trouble getting to the millimeter accuracy. My second generation of models during my PhD, I bought 300 millimeter diameter, high density polystyrene foam, which were fishing net floats. So they were millimeter accurate. And I got the fellow to plug the holes up. When he made these spheres for me, he plugged up the holes, so it then didn't become a float.
Right.
And so what I did then was that particular sinusoidal projection that you showed on my book there, I digitally increased the size, the physical size of that to match.
But where did you draw this? Because here's the chicken and egg problem, right? Yeah. The chicken and egg problem is this looks all great, but did it come from a rectangle that you sort of squashed in?
Yeah. A friend of mine, a young geologist friend of mine, he and I were on contract. And both of us were a bit light on for work. So while he was looking for work, he digitized this geological map of the world, which is in Mercator projection, rectangular Mercator projection, and converted to this sinusoidal projection. It was a whole new.
It was software. So it was a software that did that.
Yeah. That one is in digital format.
Oh, okay.
And then for each model, I increased the scale of the map. So instead of being, say, an A1 size map to fit the present day model, by the time I got to the Archaean, I was using reams and meters, tens of meters of print paper to print out this same map, and cutting it up and cutting all the bits I didn't want and just keeping the little bits that I did want and gluing them all together.
But you drew this in what? I mean, you had to draw it. how did it get into digital form? Because all this stuff on this globe obviously is printed out because was it a photograph? Then you use a drawing. Well,
that's hand digitized from the map. This friend of mine, he hand digitized it for me in map info software, and then projected that. But I was making a model. It was taking about a week to make each model. I would go into uni one day, print out the next batch of maps, come back during the week. I'd glue it all up together, and it was in coloured. So overall, there was about a fortnight, 2 week. Each model represented about 2 weeks of my life, because by the time we photographed it, and then did some Photoshop work and centering and rescaling, and I digitally rescaled it on screen to get those globes in the book, by the way.
So somebody's saying, I would like to print out one and cut out the gores and then glue it to a sphere.
Yep, I'll send you the base map, David, and you can.
Well, you know what you should do is you should put it on your website.
It is on my website.
It is. So to answer the question about doing this this part right here, this guy said, I'd like to print one out. You can go to your website and find it.
www.expansiontectonics.com. Go to free stuff, and it's in that section of free stuff in the front page.
Okay.
And it'll be
Let me see.
It's about, from memory, it's about maybe 12 or so megabytes. It's a big PDF in PDF format.
Right.
But what you have to do is you actually have to calculate the scale, your scale difference. So there is a bit of down to data. No, is it publications?
Okay. Free stuff.
Yeah, free stuff. That's it.
Oh, there it is. Download the sinusoidal map. There it is.
There you go. Bingo.
Okay. While I've got, I'm over a minute, so I can, in 30 seconds, I'm going to print this out and build one right here. No, I'm not. But yeah, I mean, people have no clue really as to how difficult it is to make those graphics. I mean, we see them and you have the Earth going around and people says, oh yeah, he made those by hand. And you're thinking, oh, that's so, why isn't it? People have no idea. That's not, we don't have the program. And I think, the program's out there. If we're smart, I really think what we need to do is to literally have meetings and talk about the software side, and maybe once a month really try to make some decisions, maybe even get some funding for it, because on a scale of 1 to 10 of software, and making Google Earth be able to do this is maybe a 2 out of 10. It isn't hard. It just isn't hard. What is hard is to move people to do it. So that's the harder problem. But anyways, I want to thank you so much, James, for having you here. Lots of people viewing this already. We get hundreds of views by a week's time, and that will only continue to grow. As you see, there's quite a few admirers, and I'd love to have more people on in this area. Like Euler is his name. What's his first name?
John Eichler.
Eichler, giant Eichler. So have John on. So let's talk with him and see if we can arrange that. That would be really great. But I want to thank you so much. We're going to be working with you hopefully in December to start getting you used to the online teaching material. It's very easy. Like I said, we're using LearnDash. So if you go to learndash.com, you write that down, you can get, I think they even have tutorials there. It is a subscription. It's not free. So, and again, if you enjoy these, please consider becoming a member. But thank you so much. Do you want to make a few closing comments before we go?
Thank you, David.
He's already said enough. What else is he going to say? Well, listen, thank you. Yeah, but thank you so much, and especially for being, it's 1 a.m., go to sleep. We'll continue to be talking, but thank you so much, and greatly appreciate it. Thank you so much.
I'm hoping to maybe put one or two more together.
Yes,
I'll
absolutely.
All right.
No. I'm sure people will not. From the views, you are a magnet to people who are critical thinkers. So thank you so much.
Thank you, David. Good night.
Okay, bye-bye. So that wraps it up, folks. It is 12:04 noon, around noontime here in Boca Raton. Of course, it's 1 a.m. in Perth, Australia. I hope you've been enjoying it, and I hope you've enjoyed James Maxlow. If you have, and really appreciate what we do here, really please think about becoming a member. You can go to our website, naturalphilosophy.org. Memberships, $35 a year. And on up, it helps pay for all of what we're doing here. If you want to read more about us in a more colloquial way, go to sciencewoke.org. But it's really, really greatly appreciate everybody's support. And if you are a member and you're watching this all the time, please consider about becoming a member and we don't have Patreon, but we do have memberships on our website, and they will be billed to you once a year. If you're a retired person, we have easy memberships for that, but it does cost us money. We have our bills coming up, and we have people doing that. So if you thought about doing it, take action now. But we're going to have more people. We're going to have Dr. Glenn Borkert's going to be back talking about infinity. We've got Stephen Bryant. He's going to be talking about his work of disrupting physics. I've been trying to get a hold of him and get him pinned down on a time, but he's already agreed to do that. James, of course, is talking about coming back, talking some more. And John Eichler, we hope to have on Expansion Tectonics. He's going to talk about mechanisms. And I really want to put together maybe a bunch of people who have proposed mechanisms, and maybe we can all talk about it. So we have I know Bill Lucas has been lurking in our green room wanting to talk about that. We can give a forum for that. So again, thank you so much for your support. I want to thank all of the Dissident Science subscribers. Really greatly appreciate your support on my YouTube channel. The idea always is to get people to become critical thinkers. We're not here to tell you the truth. The truth is something you got to find out yourself, and that's why we are here and why we exist. So remember, always stay critical, stay thinking. I'm Dave D. Hilser, your science therapist, trying to get you to the promised land of becoming a critical thinker. Ciao for now.